All right, our next set of notes. All right, so now we're looking at air resistance and terminal velocity as a piece of notes. So air resistance and terminal velocity. The first one says all objects fall at a rate of 9.8 meters per second, or meters per second squared. All right, and the mass of that object does not matter. Doesn't matter whether we're dropping an elephant, or we're dropping a piece of paper, or we're dropping a feather. All of them drop at exactly the same rate. Now, right now you're going, ain't no way. All right, but hopefully I'll be able to prove that to you in an up and coming video. All right, but right now you're just gonna have to trust me in the idea that everything falls at the same rate. All right, specifically on short distances. If we're talking really, really, really long distances, like you take a big, humongous truck and you take a feather and you drop them both out of an airplane, yep, they're gonna hit at different times. I'll agree, because that's a long ways up. But if I take a truck and a feather and I drop them both about 1 foot, so I drop them about this far, they're both going to go and hit around at exactly the same time. All right, and that's what today's notes is all about. Okay, so look at it. So we're talking about short distances of falling. All right. So all objects fall at a rate of 9.8 meters per second squared. Why is that? Well, because that's the acceleration due to gravity. That's how fast anything that falls is going to fall. Everything falls at 9.8 meters per second every second. All right, that's a number that doesn't change on the Earth. Anywhere you are on the Earth, everything falls at that same rate. So question number 2. Well, 1 kilogram equals a force of 9.8 newtons. Now, why is it 9.8 newtons? Well, the reason for that, according to your notes there, is it says force equals mass times acceleration. All right, well, then really, if we're talking about weight, well, my weight pushing down right now on this chair is the force that I'm exerting on the chair. So we can change force into W, which is weight, and that's what's in your notes. So hopefully you're getting the idea. You should be looking at your notes right now over this. So weight equals mass times acceleration. So now W equals mass. Well, what's the acceleration that's pulling down on me right now? Well, that's gravity, which is 9.8 meters per second squared. So that's my acceleration. Even though I'm not moving right now, that's what gravity is pulling me at, is 9.8 meters per second. Well, then if we assume that we're just an orange, and an orange is 1 kilogram, so now hold on, there's my light just switched off. So if we're talking about an orange, which is 1 kilogram, so I'm going to put that in for my mass. So weight equals 1 kilogram times 9.8 meters per second squared. The 1 kilogram, that's the mass of let's say the orange. Okay. And then acceleration due to gravity is 9.8 meters per second squared. That's what's pulling it down with. We multiply 1 times 9.8 gives me 9.8. Well, if you remember in the last set of notes, we said that a newton is 1 kilogram meter per second squared. Okay. Well, that's what I end up with if I multiply those things out. I get 1 kilogram and meters per second squared. So weight is 9.8 newtons. All right. All it is try and prove to you that's what newtons are. Newtons is a unit of force. Right? Instead of pounds or anything like that, we use newtons when we're talking about in science. Right? All right. So all objects are going to fall at exactly the same rate. All right. And again, we're talking about short distances. We're not talking about long distances like out of an airplane. All right. So number 3, what if another force interferes? Okay, so if I were to drop a pencil, all right, so I got a pen, and I would drop a piece of paper. I can get a piece of paper here. If I took 2 of these, all right, and I drop them right here in front of us, all right, and I drop them down, and they're just going to go, I'll lower this down so you can see, we're just going to drop them right down here onto my computer right there. That's where they're going to stop. Just below it. There we go. Okay. So now, which one of these 2 things is going to hit the computer thing first? Well, I want you to think about it. Is it going to be the pen that's over here, or is it going to be the piece of paper? So, ready? 1, 2, 3. Oh, well, the pen got there first, didn't it? All right. Well, now all of a sudden you're like, Mr. Pape, you were wrong because you said that everything falls at exactly the same rate. Yep, they did. This pen, right, and this piece of paper, they did both fall at the same rate for about this far. That was about it. All right, then there was some other force that started to push up on the bottom of the piece of paper. What was that force? That force was air resistance. Right? And because this piece of paper is so big and flat, there's a whole bunch of air that's going to push on this. And the way in which I always like to describe this is think about driving down the road in your car and you put your hand out the window while you're driving down the road. What does your arm do while you're driving down the road? It goes like this, and you're like, then also you turn it sideways, you go like that. All right. Well, what causes your hand to pull back like this? Well, it's your hand running into air particles in the air. It's air resistance. When we turn it sideways, now I got just a little bit of air resistance because it's just this part of my hand versus my whole hand. Right? So this piece of paper has lots of air resistance because we're talking about this whole area right here that's getting pushed up on. Right? Well, now what if I did it this way instead? I'm going to turn this thing and we're going to make it this way. And what I'm going to do is I'm going to drop it. I just fold it so it tries to get it to drop straight. I'm going to drop it straight this direction. So let me tip this thing down again so that you can see my computer thing. All right. Here's the pen. All right. I'm going to try and drop them both at the same height. All right. So my pen is right at the same height as the bottom of the paper. Which one's going to hit this down here first? Well, last time it was the pen. All right. So now 1, 2, 3. Which one hit? Let's do that again. All right. Let's try it again. 1, 2, 3. You notice they're both hitting it at exactly the same time. Right? It wasn't like last time where that paper went like this and then slowed up. All right, so what's the difference? Well, this little area right there, that little edge, that's the only part catching air resistance. All right? It's not like the whole paper when I did it this way where it was that whole big flat surface. Now it's just, I'll turn this towards you, it's just that little edge, so there's not much air resistance. So now they're both going to fall at exactly the same rate. All right? And that's what part number 3 is in your notes. It says, what if another force interferes? So drop a paper and a pencil. Why do they fall at different rates? Well, that was the first time. Why? Because there's air resistance pushing up on that piece of paper. All right. So that's letter B, air resistance. A force air exerts on a moving object, like your arm that's out the window of a car. All right. And then we just tried to change it so that I end up with less air resistance when I turned it this way. So I turned it sideways. Now I got less air resistance, and then now they fall at the same rate. Okay, so that's what I wanted you to get out of that. Now we go to a thing called terminal velocity, the last piece in your notes. So what in the world is terminal velocity? Well, terminal velocity is at some point, even this pen, if I dropped it out of an airplane, right, it's not going to just keep going faster, all the way until it hits the ground. No, there's going to be a point at which it's going to stop accelerating. And not meaning it's going to stop and just sit there and float. No, what it's going to do is it's not going to go faster and faster. It's going to finally hit a speed that's as fast as it's going to go. Well, what is that? Well, there's always wind pushing up on this pen. Right? When the wind pushing up, that force equals the mass of the object pushing down, then this pen stops accelerating. Right? And that's considered to be terminal velocity. That's the fastest that this pen could get to when it's falling. Right? So this piece of paper, when I dropped it flat like this, so I had this big surface, right? It gets to terminal velocity in that amount of time, a really, really short amount of time. It falls and it hits terminal velocity because it's force pushing up on all of this big piece of paper equals the mass of the piece of paper. Right? So it goes, and then it starts floating slowly because it has a upward force that equals its mass. Right? So if I'm going to go skydiving, not that I've ever gone skydiving, that's one thing I've never done. Don't plan on doing it because I don't see a good reason to jump out of a perfectly good airplane, but that's beside the point. Right? But if, let's say I did go skydiving, right? If I want to make my skydiving experience really long, right? So I don't want to go way down to the ground really, really fast, then what I'm going to do is I'm going to lay flat. All right. And if I lay flat and I wear really loose clothes so that my clothes like flap around going like that, then what's going to happen is I'm going to go slower because I'm going to hit terminal velocity a lot faster because I'm going to have air pushing up on all of my body and all the clothes and everything. And I'm going to end up going slower as I fall. Now, what if I want to go faster? If for some crazy reason I want to go really, really fast, well, then I want to stand really straight like a pencil. Then I'm going to go really, really fast because now I'm going to be like this piece of paper when I folded it and made it this way when it fell. And now I don't have much paper showing, so I don't have much air resistance. And I'm gonna go really, really, really fast. All right. Think about the idea when a person jumps out of an airplane. What do they use in order to slow themselves down before they hit the ground? Parachute, don't they? Well, is a parachute like this big? When they pull it out, it's only like that big above me? No, they're really, really, really big. It's a big old piece of paper, basically. Why is it really, really big? So, all of a sudden we get a whole bunch of air resistance, so that now all of a sudden I'm like going really, really slow, and I can go down because I got all of this air resistance of that parachute to slow me down. All right. So that's the concept of air resistance and terminal velocity. All right. And again, as long as we don't get to that point where air resistance pushes up on the object with the equal amount of force that that object's mass is, then everything falls at exactly the same rate. Right? And hopefully I'll be able to show that to you in an up and coming video here. We're going to do something that should show that to you, I hope. We'll see if we can get that to work out. So with that, we'll see you next time. Have a great day.